Swayam Prabha. Digital India. Educated India.
Hello all, welcome to lecture number 9 of this course. So in the previous lecture we were discussing about the analytical method of finding the thrust required minimum. Alright, so let us continue from there. Okay. So in the last lecture we were discussing about there are 3 points for which 2 velocities with a given value of thrust required is existing, and V is depending upon thrust to weight ratio, TR by W, thrust required to weight ratio. Second is the wing loading, and the third one is of course the drag polar. Now drag polar I have discussed extensively. Now let us talk about a little bit about TR by W and wing loading. Alright, so what do you mean by T by W? That is thrust to weight ratio. Alright, so this is the ratio of maximum available thrust to the weight of the aircraft. Okay, T by W. Now if T by W is greater than 1, so that means what? Aircraft can actually accelerate vertically. Okay, they can vertically take off. Accelerate vertically. So we have quadcopters, right? So they can actually accelerate vertically. So their thrust T by W ratio is greater than 1. Generally it will be greater than 2. Okay. So example, VTOL aircraft. So these are the examples. VTOL aircraft or even fighter aircrafts. You must have seen few fighter aircrafts have this capability. Like F-35B. They can vertically take off. So their T by W is greater than 1. And even Harrier jet. Alright, F-35 is the latest one, and Harrier one has been flying for a while now. Okay. Now if T by W is less than 1, so that means aircraft is relying on lift generated by wing. Okay, aircraft relies on lift generated by wings. So usually T by W is approximately 0.3 to 0.5. So for fixed wing aircrafts where the aircraft relies on the lift generated by the wings, the T by W is approximately 0.3 to 0.5. Okay, so this was about thrust to weight ratio. Next is wing loading. Wing loading, as the name suggests, that this is the weight of the aircraft divided by wing area. Okay, that is Newton per meter square, weight divided by area. Okay, so larger area means what? Larger area will reduce wing loading. Okay, and vice versa is also applicable, obviously. Okay, so lower W by S, that means area is more. So lower W by S actually have low stall speed. Okay, meaning how stall speed? Remember V stall was given by 2W by rho S CL. This is the square root. So V stall is directly proportional to W by S. So that means if we have lower wing loading, then Vstall will be low. Alright. So that means low Vstall means what? Meaning aircraft can fly slower. Okay. This we have already discussed before. Aircraft can fly slower before losing lift. Alright. Okay. So now we have mentioned velocity is depending upon these parameters T by W, wing loading and drag polar. V also is depending upon altitude. Okay, that you should never forget. V depends on altitude. That is by density. Okay, by rho. Okay. Now let us see this equation. Alright. Now if you see the discriminant of this equation, alright, focus on this discriminant, or let us focus on this figure. So there is only one velocity which is corresponding to thrust required minimum. Okay. Other than that, there are two velocities for two thrust required for different velocities. Alright. Now there will be only one thrust required minimum for one velocity. So that we can obtain by equating this equation, or we call it as discriminant, equals to 0. Okay. So let me write it here. When discriminant in equation 5 equals to 0, that means we obtain one solution. One solution for V. Okay. And this is corresponding to this point. Okay. This is corresponding to this point. That means velocity at which thrust required is minimum, or velocity at which L by D is maximum. Okay. Please do not forget this. This we have already discussed. Alright. Okay. So now let us proceed further and substitute that equals to 0, that is TR by W whole square minus 4 CD naught K equals to 0. Okay. I am substituting this equals to 0. Alright. So then we obtain TR by W minimum. Okay, let's not write minimum here. TR by minimum equals to 4 CD naught K. So this is equation number 6. Now we equated this equation equals to 0. Okay, so that corresponding to this point. So that point is thrust required minimum. So we can easily write over here that this condition is for thrust TR by W minimum. Alright. Now what will be the velocity corresponding to this? Okay. We are interested in finding out what is the velocity obtained from equation 5 is. So we can obtain it easily, that is V equals to 1 upon rho CD naught, okay, then TR by W minimum, W by S, and this is the square root. What did we do just now? This became 0, then we substituted this in this equation. Alright, velocity obtained from equation 5, 1 upon rho CD naught. So TR by W minimum, TR by W minimum, and then this is W by S. Okay, that is what we have mentioned over here. And this is the over square root. Alright, so if you notice this equation carefully, or you can also substitute this TR by W minimum square root of 4 CD naught K. So that means this equation will become square root of 4 CD naught K, and this is W by S, this is 1 by 2. Alright, now we can write velocity at which thrust required is minimum, or velocity at which L by D is maximum, can be written as 2 upon rho square root of K upon CD naught, or W by S. Okay. So this is equation number 7, and if you notice this equation number 7, this is the same equation that we have earlier obtained. What was the velocity required for maintaining thrust required minimum? Okay. Now this was the equation 2W by rho S CD naught by K. So we can write this equation in this format as well. Okay. 2W by S by rho CD naught by K over a square root. So those two equations are same. So hence we get same equation either by the graphical method or by this analytical method that we have just now obtained. Okay. And also we know that T by W, that we had written L upon CL upon CD, or equals to 1 upon L upon D, that is the aerodynamic ratio. So if you want to obtain T by W minimum, this should be L by D maximum. Okay, and L by D maximum, this was the equation that we obtained using equation 6. We can write square root of 4 CD naught K. 4 CD naught K. Okay. Alright, so let me write in this way. So this is, or you can write in this manner as well. So this is D by L of minimum. Okay, D by L minimum, or this again will be equals to 4 CD naught K. Hence L by D max equals to L by D max, if you write in terms of max, so then this becomes equals to 1 upon 4 CD naught K. Okay, so these are the general expressions that we obtain using the analytical evaluations. Okay, so now there are few points to note here. Okay, the first point is here value of thrust required. See this equation number 6. The value of thrust required is independent of the altitude. Okay, value of TR minimum is independent of altitude. There is no density. Okay, is independent of altitude from equation 6. But you should also remember, but the velocity at which it occurs, but the velocity at which it occurs increases with increasing altitude. Increases with increasing altitude. Why it increases? See the velocity over here. So at higher altitudes, this density becomes lower. Okay, at high altitudes, density becomes lower and then velocity increases. Okay, so the velocity at which it occurs increases with the increasing altitude. Alright, second point is K equals to, as we know, 1 by pi E AR. Okay, so higher aspect ratio, so that means lower k, and your L by D will increase. So L by D increases. The whole idea here is to see how we can increase this L by D max. Okay. And let me draw here regarding thrust required and velocity. So we have been drawing these curves in the previous lecture as well. Alright, so this was thrust required with velocity. It was applicable at a particular altitude. Okay, so for example, you can consider this is as sea level, and if you consider a higher altitude, then what happens is at higher altitude, as I said before, at high altitude, so density will be less and your velocity required will be more. Okay, so now your velocity shifts to a higher velocity over here. So for example, this curve will be applicable for higher altitude. Okay, we should keep these things in mind. This will be useful when we are discussing another topic that is we have discussed as of now related to thrust required. Okay, now let us discuss about thrust available. Okay, so we have discussed about thrust required. Also we talked about maximum velocity. Now let us focus our attention on thrust available and maximum velocity. Okay, now thrust required was what? Thrust required was W by L by T. So it is associated, it is dictated by weight of the aircraft and it is dictated by the aerodynamics, that is the aerodynamic efficiency. Already? Okay. So it is dictated by the weight of the aircraft and the aerodynamics. That is, we can broadly say it is airframe associated phenomenon. Airframe associated phenomenon. Alright, but what about thrust available? This is strictly associated with what? Strictly associated with the power plant. Okay, with the power plant or with engine of the aircraft. Okay, now let me draw the curves here for thrust available with the velocity. So this is for a reciprocating piston engine. Okay, and consider this as sonic speed, that is Mach equals to 1. Okay, so here we have a propeller rotating which is pushing the aircraft forward. So this thrust available is relatively constant, but as soon as it reaches sonic speed, it starts reducing. Okay, now let us draw the thrust available curve with velocity for a jet aircraft, a jet engine. Okay, so here mostly, okay, let me draw here again sonic speed. So here mostly thrust available is considered as constant. Okay, this is considered as constant. So let me write few points here for reciprocating piston engine. Thrust at zero velocity, so that means here at this point. Okay, thrust at zero velocity, which is also known as static thrust. Alright, thrust at zero velocity is maximum and decreases with the forward velocity. but at sonic speeds, what happens is the tips of the propeller blade blades encounter compressibility problems. Okay, and then TA, thrust available, rapidly reduces or deteriorates. Alright, so this was for reciprocating piston engine, and this reciprocating piston engine actually powers light general aviation aircraft. Alright, light general aviation aircrafts. Okay, but the jet engines, they are basically employed or basically used by all commercial and military aircrafts. Okay, so now let me draw the curve for both thrust available and thrust required to give you a brief idea. So this is, for example, thrust required. This is the velocity. Okay. Now, if we have a partial throttle available, that means the pilot has only used a partial throttle. So thrust available is curve will be in this way. That is thrust available. All right. So this is partial throttle. And if the pilot has applied the maximum throttle, this is maximum TA, maximum thrust available. So this is 0.1 and this is 0.2. Okay. So the intersection of the high speed power required curve with the thrust required curve with the thrust available curve. Okay. So that will define the maximum velocity. Okay, so let me write down here intersection of thrust required curve and maximum thrust available curve defines maximum velocity of aircraft at given altitude. Okay, so please remember this is for at a given altitude. So this will vary as the altitude changes. Okay, so always remember this is applicable for at a given altitude. All right, now analytically we can find this maximum velocity. Analytically, we can find this maximum velocity by replacing thrust required with thrust available maximum. Okay, remember this was the equation that we obtained for velocity where we had plus or minus, right? So if we remove the minus sign, we only have plus sign and replace the thrust required with maximum thrust available, then this equation will be applicable for maximum velocity. Okay, so let me write down here. So Vmax can be written here as TA max by W by S plus sign over here. Okay, so TA max by W whole square minus 4 CD naught K. In the denominator, just we have rho CD naught, and this is whole square root. Okay, so we have ignored the minus sign over here. So it looks like, and moreover, it may appear to you that if we instead of plus sign, if we write minus sign over here, so then we'll get minimum velocity. But that is not the case. Okay, so minimum velocity, remember, was governed by the stalling velocity. Minimum velocity is stalling speed. Which strongly depends upon what? Remember, which strongly depends upon CL max and W by S. Alright, so minimum velocity is governed by the stalling speed, which strongly depends upon CL max and W by S. Okay, now let us quickly go to a previous example where we had considered a jet aircraft. Okay, so here we will be adding thrust available. So thrust available was given as 16,242.5 newtons, right? But this was for one engine. So for both engines, we can write thrust available equals to 16,242.5 into 2. So this becomes 32,485 newtons. Alright. So to fly at maximum velocity, pilot has adjusted the throttle such that thrust available equals to 32,485 newtons. Okay. Now we have already drawn the thrust required with velocity curve. Remember? Okay. Now let us go to the MATLAB plot and let us see what is the velocity at which we have thrust available is 32,485 newtons. Okay. Now let us check that. Okay, so this was the code that we had written in the last lecture. So let me rerun this code, and this is the curve that is thrust required with velocity. All right. So we were discussing that at the thrust available, which is around 32,485 newtons. Let me hover around here. So this is 32,000. Okay, 32,200 plus 32,500. Okay, so at around 32,500 Newton, the velocity it has to travel at approximately 300 meters per second. Okay, now the equation that we have derived, now let us write a code for this and obtain the intersection of thrust available and thrust required curve. Alright, so now let me just copy this that we had written in the last class. Okay, alright. And we'll be also be plotting the maximum velocity analytically. We'll be finding it rather. Okay. Now let me, after CD, let me write here thrust available in newtons. In newtons. Alright. So thrust available equals to 16,242.5 into 2. This is our thrust available. Alright. Now let me find what is the maximum velocity using the analytical expression. Okay, so this was the expression for the maximum velocity. So this is the expression for the maximum velocity. So this I will be writing over here in the code. Anyhow, in the plot we can easily see what is that the velocity was around 300 meters per second. So let me break this into two. Let me write this as term 1, this as term 2. So this whole divided by rho CD naught. Okay, so let me write this as term 1. So TA by W into W by S. To W by S. Term 2 is W by S into square root of TA by W whole square minus 4 into CD naught into K. Okay, to CD naught into K. That's it. Okay, now we have term 1 and term 2. Now we'll be finding Vmax. So Vmax equals to square root of term 1 plus term 2 alright, then divided by, in the denominator we had rho into CD naught. Okay, rho into CD naught. Alright, it is saying it has not used Vmax. Okay, since it has the same name. Okay, so let me change it to V capital max, Vmax. Alright, now it is fine. Now in the plot we'll also be plotting a thrust available. Okay, so we can directly modify this plot here. So after plot V comma TR, let me write here Y line. So it will be plotting thrust available TA comma red color 2 dotted lines and line width of 2. Line width of 2. I will also like to label it as thrust available. How much? 32,485 newtons. Alright. Okay. Now let us see what it has got for us. I am saving it and I am running the code. Now see here, this was actually, we saw it earlier that around 300 meters per second we are having the high speed intersection of thrust required curve with the thrust available. Alright, now if you focus here, it is around again approximately 300 meters per second. Alright. So if we plot a data point over here, alright, so at approximately 298 meters per second, we have this maximum thrust available. Okay, now let me just close this figure and let us check the analytical calculation for this Vmax. So you can see here, so Vmax is approximately 298.63 meters per second. So the expression that we have actually derived is actually correct. Okay. So this is the maximum velocity using the analytical expression. This is the maximum velocity. Alright. And one more thing, if I plot this again, as I mentioned before, so even if I extend this plot to get the minimum velocity, alright, so I have started the velocity vector at 15 meters per second. So if I change it to say 22, Alright, save the code and run it. So the intersection of this doesn't mean that this is the minimum velocity with which the aircraft can fly. Okay, so here it is saying only 24.7 meters per second. So this minimum speed is governed by the stalling speed, not this intersection. Okay, the minimum speed is governed by the Vstall and the CL max. Alright, so let me just change it here. So here we have 50, and you can plot to 350 also. Let me rerun the code. Okay, so here I am not able to see beyond 300 because I have mentioned here 300. Save it and then run it. Now you can able to see here. Alright, it is going till 350. Alright, but we are interested only over till around 300, since this is the maximum velocity with which the aircraft can fly. Okay. And I am saving this as V maximum. Okay. Alright. Now let us quickly begin with our next topic, that is power required for level unaccelerated flight. Okay, so till now we were discussing about thrust required for level unaccelerated flight. Now let us talk about the power required for level unaccelerated flight. Okay, so why do we need to discuss power required? Till now we have been discussing about thrust required because the conventional jet engines are rated in terms of thrust. Alright, hence the TR curves were useful. For performance analysis. Alright, this for jet aircraft. But what about piston engines? For piston engines, these are rated in terms of horsepower or power. Okay, hence power required and power available are more relevant quantities. Okay, and also if we do not even consider piston engines, but still power is relevant quantity because consideration of power leads to the calculation of rate of climb, maximum altitude, for both jet as well as piston engine. Okay, now what is rate of climb? That we'll be discussing in the coming classes. So generally speaking, so power required, power available becomes more relevant when we want to find the aircraft performance in terms of rate of climb or maximum altitude. Alright, so let us discuss a little bit about power. So power is nothing but energy upon time. Energy is force into distance upon time. So this we can mention force into what is distance upon time. This is speed or velocity if direction is also known. Okay, so force into velocity. So power equals to force into velocity. So for an aircraft, what is the force? So for an aircraft, thrust required is the force. Okay, so hence we can write power required equals to thrust required into velocity. Let us continue our numbering. So this is equation number 10. So the PR is power required. Okay, PR is power required. Now let us start doing graphical approach like we did for thrust. Okay, graphical approach. So graphical approach, now again here we are interested in the curves, that is power versus velocity. Okay, so the graphical plot of power required versus velocity for a given aircraft at a given altitude. Okay, for a given aircraft at given altitude. Please remember those all curves are applicable for particular altitude. Okay, this is called power required curve. So power required curve is obtained by using equation number 10. Now remember we formed a table in one of the earlier examples where we had formed the CL by CD and then thrust required, right? So we can form another table where we just have to add, this was the table V, CL, CD, CL by CD and then thrust required. Okay, now here we can add power required as well. Okay, so power required is nothing but thrust required into velocity. Okay, fine. Okay, now let me write here. So power required, because thrust required into velocity. Okay, we had obtained for 50 meters per second. Let me write numbers here. 9493, 0.1868, 10.4352, 8449. So this was the analytical numbers that we obtained. Now what will be the power required? Power required will be thrust required into velocity. So that is 8449.93. Velocity we started with actually 50 meters per second. So 422,496.69. Okay. Now what is the unit of this, by the way? See, power required is thrust required into velocity, correct? So thrust required we write in newtons, velocity we write in meters per second. Now what is Newton meters per second? That is 1 watt. Okay, so this is 1 watt. Now if you want to convert to kilowatt, 10 to the power minus 3 kilowatt. So whatever answer that we have obtained, that was Newton meters per second or watt, you just have to multiply by 10 power minus 3 to convert it to kilowatt. Okay, so this becomes 422.496 kilowatt. Okay, so here we will get 422.496 kilowatt. Okay, now let us again go back to MATLAB and see how we are getting the power required curve, right? So now this is the Vmax that we had obtained in the previous plot. So let me just copy this code and modify this. Alright, and I've renamed it as power required curve. Okay, so now let me just, okay, let us write here approximately velocity starting from 35 meters per second. Alright, this is the velocity at which thrust required is minimum, term 1 plus 2. Okay, now let us write here power required. Power required. Okay, so that I am denoting it as PR equals to, I'll write here thrust required into velocity, thrust required into dot, remember dot into V is a vector. Okay, thrust required into velocity and we will directly convert it into kilowatt. Okay, in kilowatt. Fine. Now let me write this as figure number 1. Alright, in figure 1 it is velocity with thrust required, rest everything is remains same. And in figure 2 let us plot PR, power required, with velocity. Alright, so let me write here, let me copy this here. So we have figure 2, this will be figure 2, and we need velocity with power required. Power required, let me note this by the black color. Line width is 1.5, and this we do not need now. Y line. Okay, X label is velocity, and in Y label we have power required. Power required will be in kilowatts. Okay, and in title 2 you can mention power required versus velocity. Power required versus velocity is read on. Alright, let me save this. Let us see if there is any error. Alright, so this was figure 1, and now this is figure 2. Okay, so this more or less curve looks like similar only. Okay, it looks similar, but exactly it is not. So what we'll do is we'll plot these both figures, figure 1 and figure 2, in one plot. Okay, then we'll get to know what exactly is going on. Okay, now there is another method that we can plot these two curves in one figure itself. Okay, even though the magnitudes are different, so there is a way to do that as well. So let me write here combined plot. Let me write here figure 3. Alright, so the left axis will be your thrust required, and the right axis will be your power required. Okay, so we will write here y axis left. Alright, now here we will be plotting velocity with thrust required. Let me just copy from here, velocity with thrust required. Velocity with thrust required 1.5, and here y label, actually that can also be copied. Y label is thrust required. And let me denote the limits to y limit. Okay, let me write here 0 to maximum of thrust required. Okay, maximum of thrust required, I am multiplying by 1.1 so that it can be easily viewable. Alright, okay, now we are done with the y-axis left. Now let us see y-axis right. Okay, and the same plot, y-axis right. So here we'll be having plot v comma pr, plot v comma pr p. Okay, let me write here with a dotted line, b dot dot. Fine. Now y label will be power required in kilowatts. Okay, and let me put y limit here as well. Y limit here as well, 0 to max of PR. Okay, And then finally, what is in the x-axis? X label velocity, meters per second. And title also you can mention. Title you can mention as comparison of thrust and power required versus velocity. Okay. Now since there are multiple terms, let me write here a legend. Okay. The first is the thrust required. Second is the power required. And we can also denote at what location do we want. Okay. So for that we can easily mention location as best. Alright, so MATLAB automatically changes the location of this legend as per the space available. Grid on, and let me define x limit here as well. So 0 to, let me write 350. So let us see. Okay, let me also write here maybe 350. Okay, Control S, and let me run this code. Okay. All right. So this figure 1 and figure 2 we had already seen. So the idea behind figure 3 was we wanted to see what exactly is happening over here. So if you see in thrust required, the thrust required, minimum thrust required is coming at around 80 meters per second. But what about power required? So there is some difference you are able to see over here. Alright, the power required minimum and the thrust required minimum, they are not at the same place. Alright, so this in figure 3, the velocity for which power required minimum is actually less than the velocity for thrust required minimum. Okay, now what is the reason for this? Okay, so that is what we will discuss now. Okay. Okay, so we saw that velocity for which power required is minimum is less than velocity for which thrust required is minimum. Okay, now what could be the reason? Now let us see quickly analytical approach. Alright, so power required, we know this is thrust required into velocity, and for level unaccelerated flight we know thrust required equals to W by L by D. Okay, and lift is equals to weight equals to half rho V square SCL. So what is the velocity? 2W by rho S CL. So power required we can mention here as W by CL by CD into velocity. The velocity is 2W by rho S CL. So power required can be written as 2W cube CD square upon rho S CL cube. So this is an equation for power required. For lift is equals to weight. Okay. So now if you see this equation carefully, so power required is inversely proportional to CL power 3 by 2 by CD. Okay. But remember, what about thrust required? Thrust required was proportional to 1 upon CL upon CD. Okay. So for power required, so we have been discussing about thrust required minimum. Now let us discuss about power required minimum. So power required minimum, we need this CD by CL power 3 by 2 to be minimum. Okay, or we need CL power 3 by 2 by CD maximum. Alright, now let me draw the plot here. This is the power required and this is the velocity. So let me draw the curve here, that is V. So this is the power required minimum. Alright, and this is the velocity at which not CL by CD is maximum, velocity at which CL power 3 by 2 by CD is maximum. Okay, or velocity at which power required is minimum. Okay, so that is why these curves were not matching with each other. Okay, so for thrust required minimum, it was proportional to 1 by CL upon CD. So that means for thrust required minimum, it was 1 upon CL upon CD. Okay, this was maximum, and in this case, this is CL power 3 by 2 by CD maximum. Okay, that is why these both curves are not matching. Alright, so these both look similar expressions, but similar, but they are different expressions holds for power required minimum. Okay, so here again power required actually first decreases as the velocity increases. This becomes minimum and then again starts increasing. Okay, so here this curve looks similar to the thrust required curve, but exactly it is not the same. So power required minimum is applicable when CL power 3 by 2 by CD is maximum. Okay, and the reason why the power required is behaving or the curve is in this fashion, that we will discuss in the next lecture. Thank you.